Welcome to the AI Research Roundup. I'm your host, Alex. Today is May 10th, 2025. We're discussing an ICLR conference paper published about 3.5 months ago on January 22nd, titled, How Much of My Dataset Did You Use? Quantitative Data Usage Inference in Machine Learning. This paper tackles a key question. How much of a dataset was actually used to train a model? It introduces dataset usage cardinality inference, or DUCI, a way to get a precise percentage. This moves beyond simple yes-no checks by refining membership inference, which are methods to guess if individual data points were used in training. Alright, so building on that idea of refining membership inference, this first figure really illustrates the problem with older approaches. These methods are primarily binary, meaning they typically just indicate if, say, all of a dataset was used, or none of it. The figure shows two such prior techniques, dataset inference and backdoor watermarking. As you can see, when the actual proportion of data used changes, their predictions for dataset usage just jump wildly between 0 and 1. This really shows why we need a more nuanced tool, like the proposed dataset usage cardinality inference, to get an actual percentage. Alright, moving to the results. This table really drives home the effectiveness of their proposed dataset usage cardinality inference. It shows the maximum mean absolute error, or MAE, a score where lower is better, measuring the average prediction error for dataset usage percentage. Across various datasets and models, their method, labeled hours, consistently achieves a much lower maximum mean absolute error, those bolded numbers, than simpler membership inference aggregation baselines like MIA guess or MIA score. Impressively, the maximum mean absolute error is often below 0.1, even with very few reference models, which are pre-trained models for calibration, and this performance is close to far more costly maximum likelihood estimate, or MLE, approaches, which are standard but intensive statistical estimation techniques. Okay, so this next figure further illustrates the efficiency and accuracy we just saw. It plots that maximum mean absolute error we discussed against the number of reference models used. You can see the red line representing their method stays consistently low, achieving that desirable sub-0.1 error even with just one single reference model. This is a stark contrast to other simpler membership inference aggregation approaches. And importantly, their method performs comparably to the much more computationally demanding maximum likelihood estimate methods, which, as you can see, require many more reference models to even begin operating, indicated by that vertical dotted line. Building on that efficiency, this next figure looks at how well their method quantifies the uncertainty of its estimates using confidence intervals. A confidence interval is essentially a predicted range of values that's likely to contain the true answer, here the true dataset usage proportion, with a certain probability, like 95%. The top plot shows excellent coverage across different true proportions of used data, meaning the true proportion nearly always falls within their calculated 95% confidence interval. The bottom plot then shows these intervals are also quite tight, with an average width around 0.1 to 0.14, indicating good precision in capturing that uncertainty. So taking this precision into a very practical scenario, this table shows how their method performs when trying to quantify book copyright infringement in language models. We're looking at the mean absolute error again, so lower numbers are better here. Across different proportions of book data actually used for training, their method, labeled our method, consistently shows a much lower error. For instance, its maximum mean absolute error is just 0.1684. Significantly better than the 0.3350 or 0.5019 from the other simpler membership inference aggregation approaches. This really demonstrates its real-world utility. Okay, and to further underscore the reliability of their underlying signal detection, this table presents p-values for different methods. A p-value is a statistical measure. A very small p-value when a dataset is used indicates strong evidence the method correctly detected its presence. Conversely, a p-value close to 1 when a dataset isn't used means the method correctly identifies no usage. Here, their method ours shows an extremely small p-value, the 3.15 times 10 to the minus 51 when the dataset was used, and a perfect 1.0 when it wasn't, indicating very high confidence. Alright, So in conclusion, this work really tackles a vital question. Not just if data was used to train a model, but how much. The authors achieved this through what they call Dataset Usage Cardinality Inference. This is their method for precisely estimating the proportion of a specific dataset that went into training a model. We've seen it's highly accurate, efficient, and provides reliable confidence in its estimates, a big step for AI auditing. That's our roundup for today. Thanks for listening.